Thank you, Gael. So I will speak about the sea level rise and coastal hazards. Um, whoops. Okay, so next slide. So this material is coming from an ESA contract, which I launched and steered in the last 2 years, called Earth Observation Advanced Science Tools for Sea Level Extreme Events, EOATC. And basically, I would like to remind you that the coasts are crucial for humanity, with 40% of the global population living within 100 kilometers from the coast. And they face growing threats from climate change, like rising sea levels, coastal erosion, extreme weather. And managing these vulnerabilities demand a comprehensive monitoring to ensure sustainability, disaster risk reduction, and scientific knowledge of processes. And satellite plays an indispensable role in monitoring coastal dynamics, providing global high-resolution data on parameters such as sea level, wind, waves, and etc. And you remember what just happened in Valencia, and we have an example here in South Brazil, where there was a dramatic flooding event. It was the fourth climate disaster in 1 year in this area, the South Rio Grande do Sul. And so basically what happens is you get extreme precipitation, you get strong wind pushing the water to the coast, and also a storm surge, which rises further the sea level. And okay. I'm sorry, the buttons don't appear. Why did the buttons? Okay, then now they appear. Okay, so let me just try to find. Okay, so the objective of the project was to bring together Earth observation experts and coastal modelers to perform a reconstruction, a data-driven reconstruction of extreme sea level events, and enhance the scientific understanding and predictive capacity of ESLs, and better prepare for impacts and risks of the ESL events. And so we started with a requirement analysis. We needed to identify the needs. So we started with a literature review to define the main scientific challenges. Then we had an expert discussion to assess the potential methods and feasibility within this project, which is always limited in resources and time. And then we organized a scientific workshop requirement to co-design our project with users. We had a very strong participation, to more than 200 people from 42 different countries, and everybody requested the recording so they could look at it afterwards. And so out of the 80 requirements, we prioritized, and we chose, because of limited resources, the two major ones. And we looked at the priorities and what people were asking for. Essentially, it dealt with accuracy and the capacity of the system, and the design characteristics. So we went on and we gathered an extreme experimental data set, and we located on 6 different use cases, like the Dutch coast, the Adriatic Sea, the Tagus estuary in Lisbon in Portugal, and the Azore Islands, and the northeast coast of Madagascar, and also the Marshall Islands in the Pacific. And so this data set, basically, this is a very important slide because it's the data that you might want to be looking for if you want to do on such an application. And so we looked at the short-term processes and also analyzed the long-term processes in order to give some insight of what could happen in the future. So bathymetry, topography, land use, land cover, we just heard about. Vertical land motion also is a very important contribution to sea level rise. the absolute sea level rise, the relative sea level, the tide, storm surge, waves, and so on. River discharge also, and flood mapping. For the long term, we looked at shoreline position and many other important things like the potential storm surge flood map. So the scientific approach, basically, so we had these 6 use cases, and we looked at the short term and the long term, so both requires modeling. And we constructed the TWL. So this is the important acronym that you should remember all throughout this presentation. So it's a total water level. We looked at specific events, and we looked at constructing a 20-year time series and analyzed what we got. And for the long term, we looked at historical trends. So the sign cases were based on predictability. We're focused on predictability, the process understanding, and the risk and vulnerability assessment. So the scientific challenges were the drivers of extreme sea level and the nonlinear interactions. It's a complex compound system, so there are interactions between the different drivers. Then the dynamic morphological response to the coast to extreme events like coastal erosion, and the extreme sea level and the tipping points for coastal impacts to look into the long term. So the scientific highlights coming out of this project. So we reconstructed the total water level. So it's basically the sum of the astronomical tide and the storm surge, the sea level anomaly, and the wave run-up. So, for instance, sea level anomaly here, we have satellite radar altimetry satellite tracks, which allow us to build this component. So we'll see the component one by one. So here you have, you start with the mean sea level, and then you take into account land subsidence. So basically the land goes down, and then things go up, like the relative sea level size. The tide goes up and down with different amplitude and variation amplitude across time. The seasonal sea level anomaly, basically the normal, they say the mesoscale anomaly, of course, but also seasonal oscillations like El Nino or the North Atlantic Oscillation. And then there's the wave. So the wave basically, well, there's a storm surge here, and due to, for instance, the atmospheric pressure lowering, so the water goes up if there's no pressure pushing it down. And then the wave setup and the swash, so the total of setup and swash is called the run-up. And so we'll see this in detail. So storm surge comes from the Mode 2D dynamic atmospheric correction, which is developed at Lagos in Toulouse. The atmospheric tide also comes from the FES model developed at Lagos in Toulouse. Then the wave run-up, we tried 2 different models. The wave earth model, which is essentially wave height and wave period, plus taking account of the beach slope. And we looked at the Stockton model as well, which provides also an estimate of the run-up. So the sea level anomaly, it comes from Extract, which is also coming from Lagos in Toulouse. And we use all the satellites that you can see here on this map, all the radar altimetry satellites available, and which allows us to have a very high temporal resolution. Like, for instance, if you take the Adriatic Sea here, you have a couple days of revisit time. And we checked the binning, like 1 degree, 2 degrees, and so on. And we have a very significant number of samples to build this sea level anomaly. So the use case I told you about, basically, they are low-lying coastal environments with high exposure time. And this covers the enclosed sea, the open coast, and the oceanic islands. And so this is an animation of, here you see the run-up, and in purple, and you see the storm surge, the sea level anomaly. This is the tide in orange, and the total water level in blue here. You can see it with this visualization. You can zoom, you can do averages, and you can see, for instance, you can zoom, like, for instance, around November 2005 here, you have an idea of what the total water level looks like. Basically, this is the zero here, and so the tide makes everything oscillate, but then with the storm surge, you have peaks up to 2 meters. So then we wanted to do the flood risk assessment. So we used 6 different digital elevation model, and we tried and we produced different flooding scenarios. You can look at which one here on the slides. Then we saw that not all the dams are capable of capturing the connectivity and the way that the flood is going to happen at the coast. And so pick the right one. And then we look at the influence of shallow water. So we have this historical evolution of shallow water made by satellite-derived bathymetry. And this animation shows you the different types of waves that hit the coast here. And you see here there's overtopping. And we did that for different storm events, and basically where the water level was also around 2 meters. We looked at the satellite derived topo and bathymetry. We focused on one of the atolls of the Marshall Islands here, and you see in the movie here you use the Sentinel-2, then you derive the bathymetry, you compare with worldview, and you look at the bathymetry evolution, and basically all the scenarios that we produced with this bathymetry and topography, they were more or less in line within 30%. We could do better. Then so basically, the scientific outcome from this activity, we looked at satellite-derived bathymetry, which has a very important impact on how the flood is going to happen, especially for the wave run-up. We reconstructed the total water level at specific times in high resolution and in the long term to see the trends. We also looked at the shorelines, the evolution of the shorelines. And we compared the altimetry with the different models. And you can see in those 3 plots here that the model and the altimetry are doing pretty good. So the model is a good way to interpolate the bathymetry when the satellites there. So we produced reports for different technical reports. We presented in different places. We're producing now 9 scientific manuscripts, and I'll show you also that you can also publish your paper in a special issue. So the main challenges and the limitation coming from this work is that topographic and bathymetric data in high resolution are very important. It's crucial for modeling the coastal processes for extreme events. The increased spatial, especially temporal resolution is very important for monitoring the drivers and looking at the impact, like flooding, of course. And the EO-based measurements, like sea level, waves, and wind, they need to be retrieved a little bit closer to the coast. So like altimetry is difficult to do close to the coast due to the presence of the coast, which is polluting the measurement. And some variables from Earth observation are not available, and in situ data also is widely not available, not well shared. And like, for instance, wave run-up is difficult to gather. Just a word on model. Of course, it's a complex problem, so it requires a multidisciplinary approach. And for the short-term simulations, we could incorporate more nonlinear interactions, considering the complex and compound nature of extreme events. So we looked at societal impact, and the challenges are associated with scaling up, and particularly in terms of ensuring data consistency and model performance across different regions. The operational framework is necessary to provide this as a service. And the coastal vulnerability index also is important. So we ended up with a roadmap. Basically, everything is going to be consigned in this special issue. Then we are promoting these results at different conferences, like one in Brazil, the Living Planet Symposium of ESA, the COSPAR Scientific Assembly of COSPAR, and publishing more digital content. But basically, we need to go towards an operational supply chain, and we certainly need to improve our skills. So foster more research to develop next generation of total water level products, and we need to work on improving individual components and eventually adding new enhancements and current limitations. So there's work to do. So. Which should lead to an operational concept, which is a pathway for adaptation within digital twins. And so it's a multi-source problem to cover multi-hazard and look at multi-impact like erosion and flooding. And it's a multi-scale. We need to provide early warning, but we need to understand the long-term risk. Hazard observation and forecast needs to be done with numerical modeling, which are data-driven. And also the morphology part requires also a forecast if you want to help people take decisions about protecting the coast at national scale, at local scale, and look at the short-term events and be aware of what's going to happen in the long term. So this is the special issue in which we're going to publish nine papers from this contract. And you're also, if you work in this domain and want to publish here, I think it's a good place, the International Journal of Applied Earth Observation and Geoinformation. Deadline is 15 February 2025. And I would like to say that in WEkEO, you can find data sets. Not all of the data sets that I showed you that we have used are yet found in WEkEO, but they might be in the future, especially if there's some demand. Of course, altimetry for Sentinel-3, Sentinel-6, and oops, doesn't move. Okay, so okay. And so also wave height you can get from WEkEO, and you can make a beautiful map with the tools that was presented earlier. This is of the 2nd of December, the map in the Mediterranean Sea of wave heights. And I advise you to stay tuned to the ESA Extreme and Disaster Science Cluster. It was launched to promote networking, and it involves several ESA-funded projects. If you want to apply for a postdoc and work in this group, go to EO for Society at esa.int. And I'm done here, and thank you very much. Don't hesitate to contact the people that did the work under my my leadership, and myself if you want more about this. Thank you.
Thank you very much, Jérôme, for your nice presentation. It was a huge hit in the chat, so lots of people were happy with it. So we are going to move on to the few questions that we have. So, first question, how accurate is the satellite derived bathymetry?
So it's an interesting question. It really depends on the target, and it depends on the depth. So it works only with very little depth, and so the accuracy depends on the depth that you are looking at. So I would say from 1 meter to 5 meters, depending on the depth.
Okay, thanks a lot. So this one is not the question, it's to congratulate you on your presentation, which was really nice. Next question, what is the reason behind selecting the particular study areas?
Well, we had a long discussion, especially in the user requirement part and during the workshop where we had 100 people logged in. Not as successful as this workshop, which is had 700 people, which is quite impressive. So congratulations to WEkEO. So basically, you understood that we want to check the different kinds of morphology. So enclosed seas, open island, and vulnerable coasts. And this is why we ended up with these different regions. A few in Europe because we are quite interested in Europe, but also we wanted to look at the very low-lying islands in the Pacific, like so we took Marshall Island as an example, also because we had some in situ data. Because in situ data are very important in order to really work with Earth observation from space. And any place where there is access to in situ data is very comforting because you can do validation of what you're doing.
Thanks a lot for the explanation. So the next question, so interesting presentation, where the DAM8 converted from the reference JOE to MSL MDT.
So the DEM are reference to an absolute reference ellipsoid, like the GPS one, like the WGS84, and that gives us the absolute height. So then you're talking about the land DEM. So we use absolute heights. And then you wonder, where is the mean sea level? And so, yes, this is given as a mean sea level map. So it's a geoid plus the absolute topography.
Thanks a lot. So next question. Does the wind direction depend on TWL?
Well, I would probably revert the question. Does the TWL depend on the wind direction? Because we don't really control the wind direction. It just happens. And basically, when you get, like in the Brazilian example I showed at the beginning, you get the wind pushing the water towards the coast, and you get a higher sea level anomaly. And so the wind will create a modulation of the total water level.
Yeah, exactly. Thanks. And so this question about if the storm surge data was from WEkEO. So it was the part where you talked about.
This is a question I'm not sure I can answer myself because I don't know all the data set. And they're so numerous. But I showed you that you get sea level anomaly from WEkEO. And you get also the waves, which is an input for the run-up models. And also, well, you want to know the storm surge part. It comes from this dynamic atmospheric model, which is at Lagos, called MOG2D. And you find this data in the altimetry data. It's one of the parameters in the NetCDF files with the altimetry.
Thanks a lot. So we have several questions. So I will read this one. What is the link to apply for ESA EO postdoc opportunity you mentioned? So we have several questions about that. The PDF presentation will be made available. You will be able to find the details about this offer. So do not worry, but maybe if you want to add some extra detail about that.
Well, basically, if you go to EO4, the number 4, society.esa.int, you see everything we do in R&D for Earth observation. And here you will have also announcements about opportunities for doing a postdoc in the science hub, where there's these clusters, ocean cluster, the hydrology cluster, and the extreme and disaster cluster. So EO number 4 society.esa.int.
Okay. Thanks a lot. Maybe we can also put the link in the chat for everyone to see. Thanks. So next question.
What
Was
is
it sorry. What is satellite track if you make an AI for processing image? Will be that possible? Would it be that possible? And will it make your work easier?
Yeah, so we use AI all over the science hub at EO for Society, Earth Observation for Society. The satellite track is just the fact that the radar altimeter is measuring right under at nadir, and so we have a track. You know, imagine um, just like you know when you roll a ball of wool, you have this wool thread, and so this is the track. So it's a flight of the satellite, and so we get data under the satellite. And now we have launched a beautiful jewel of altimetry, which is a two-dimensional instrument called surface water ocean topography, so SWOT, and that makes a two-dimensional map. So it's not just a track; it's also a map. But that's really new. And so yes, we use AI. We use AI at different level of the processing, and yes, it will make our work easy as long as we control what the AI is doing. Of course, we have to be very careful with AI, and sometimes we don't understand what it does, but the output seems quite plausible.
Okay. Thanks a lot for the explanation. This one question asking if it is applicable for both metropolitan and rural areas.
Yeah, so the different digital elevation model or digital terrain models allow us to see how the flood is going to take place and how the water is going to be circulating within the city, for instance, when flood appears in the city. And so this is what I call connectivity, where so yes, there are models which are developed to see step by step how the water is going to invade an urban area. And of course, rural areas are probably easier because the digital elevation model and the terrain model is much simpler because there's not much buildings and so on. So yes, we in the 6 DMs I showed, you could see the buildings, you could see the streets, and you could see how the water propagates during the flooding event.
Thanks a lot. So we have time for 2 more questions, if it's okay with you. So the almost last one is if you could quickly explain about the morphological evolution due to ESL events.
Well, this is essentially linked to coastal erosion, and we know that coastal erosion happens in steps. After a big storm, there's a drastic change of the coastline, and so this is the evolution. We follow the coastline year after year with satellite images, and also we look at the movement of the sandbanks with satellite derived bathymetry. And this is one of the slides. Also, you can go back to it and look at it, where we follow the evolution of sandbanks, which has an impact on the wave breaking and the wave run-up.
Thanks a lot. So now the last question for you for today, or more of an open question: how can local governments integrate sea level rise projections into urban planning and development?
Well, this is a very hot topic, and you know, for instance, in France, after the big storms that we had at the end of the last century, the President Sarkozy developed a plan, and for instance, it became illegal to build houses too close to the shoreline, and so on, especially in vulnerable areas like the islands that we have in the French facade. And the French facade itself. And so, yes, they do integrate sea level rise projection, risk analysis, vulnerability analysis, and the mayors and the prefects and the central government in Paris deliver construction permit or not, and most likely not. they produce a map where you have red, orange, and white, and where you can develop urban buildings or houses and so on. Yes. So it is taken into account, and all the governments rely on this kind of data to allow construction or not, and also to develop protections. Millions of euro are spent just on the French facade, but so many millions it comes to. I mean, maybe 5 million for 10 kilometers of protection. So you can imagine how much money is invested in order to protect the coast. And this is paid by the taxpayers of the whole country for the people who live near the coast. But same thing for landslides and things that happen in the mountains, and avalanches and so on. So yes, the government of many countries are very concerned by this. And
yeah, exactly. Well, thanks a lot for all of the Q&A. Thanks also for your presentation. And thanks again for